Last time we'd introduced systems of linear equations, but we didn't actually discuss how to solve them. So this time we are actually going to go through the algorithm that we use to solve linear systems. I've written 3 different examples of linear systems here, and the first type of system, we're going to call it diagonal form, because if I align them here, you can see that there's a diagonal line going across. This type of system requires no work to solve, because you can just read off the solutions from the equations themselves. Diagonal form would be our goal. Now, we'll never get so lucky as to get a system in diagonal form to begin with, so instead we're going to try to see what else can be done. The next type of system is also pretty good. This is a system that is in triangular form. Triangular form is not as good as diagonal, but it's still pretty easy. From the last equation, you can see that z is 1. The second equation will allow us to solve for y really easily, because if we know z, then we can just plug in the value of z to get y is 2. From the top equation, we can easily figure out the x as well, a -1. Now, generally, we won't have either of these. Our goal today is to convert a system into diagonal form if possible. What we're going to do is make our system look different, but have the same solutions that it had at the beginning. So we are going to try to convert it to an equivalent diagonal form, an equivalent simpler form. Now remember from last time, the word equivalent means same solution set. To do this, we are going to talk about what are called row operations. These row operations will preserve the solution set, but make the system look different. And by looking different, I mean simpler or closer to a diagonal system. And there are only 3 operations that we are going to use. Now, as an example, to try to motivate this, a system of 2 equations with 2 unknowns, we could write it in this standard form, or we could put it into augmented matrix form. So this is the coefficient matrix, and this is the right-hand side. So the first thing that you're allowed to do is to swap equations, and it won't change the solution set. So if I label this equation 1 and I label this equation 2, you are free to swap the order in which equations are written. The answers to the system will stay the same. We're going to use this squiggle to represent equivalent. So if I put this squiggle between systems in standard form or in augmented matrix form, it doesn't say that the 2 are equal, but they're just equivalent in the sense that they have the same solutions. Now we call them row swaps because in a matrix form, each equation is represented by a row. The second thing that we can do is row scale. I'm allowed to multiply both sides of an equation by the same number, and it won't change the answer. So I can multiply the same value on both sides of a single equation or row. Now, as an example from my system above, if I started with x plus y is 1, x minus y is 2, I could take this first equation, multiply this side by 3, and if I want to make sure it has the same solution set, I have to do the same thing to the other side. So in this case, I'd be taking 3 times row 1 and making it the new row 1. In matrix form, this is going to look like 3 bunches of 1 going into the new one. I'll have a 3, 3, 3, 1, -1, and 2. So those 2 systems look different, but they are going to have the same solution set. Now, the third thing that we can do is what's called row replacement. You are adding the same value to both sides of an equation. If I take that same example that I've been working on, if I felt like it, I could add a 2 to this side of the equation. And as long as I do the same thing on the other side, it will be equivalent. They will have the same solutions. Now you might say, well, why would you want to do that? And here's the key. This is not a single linear equation in isolation. It's an equation as part of a system. And in this system, 2 has an alternate form. 2 could be swapped out with x minus y. The reason I add 2 to both sides is because I want to switch the stuff on the left to an x minus y. Why do I want to do that? Because those y's will cancel out, and that will make my equation look really simple. Row replacement is a way of eliminating variables if you need to. The net effect is that we added these equations. So we added 2 to 1, and that replaced 1. And so the system that I started with, if I take equation 2 and add it to 1, it will become the new equation 1. The system will be equivalent, but it will look like this. That's a much better looking system because I've got a single variable, x, by itself over there. You could see that I could do the triangular format that I talked about earlier. So we are going to use these 3 operations to change any linear system into as close to diagonal as possible. Now, there's an algorithm that we are going to use to do this. An algorithm is a prescribed set of steps that you repeat for any situation. And this algorithm is going to be called Gaussian elimination, named after Gauss, the really famous and talented mathematician. Now, we're going to start introducing this notation. We're going to represent an augmented matrix with a bunch of x's, and x just represents a number that is not 0, and perform these row operations to eventually turn it into something that looks triangular. I'm going to put zeros in when I want to be very clear that it's a 0. And then eventually I would love to turn it into something that's diagonal. Now, if we leave a blank, that means that it's a 0. So if we get lazy and we don't want to write in the zeros, we can just leave them blank. In the next video, we're going to talk about how to do this.